introduction. Good afternoon, dear colleagues, dear ladies and gentlemen. My name is Benedek and it's my pleasure to present the work of my colleagues and myself in the highlighted topic. Here you can see the overview of my presentation. This research was conducted inside the STUMAT-LTO European Research Project. And in our task, our aim was to determine fracture toughness values from a simulation environment, which is very helpful in the lifetime assessment of nuclear power plants as well. And for that purpose, we aimed to do material tests, also small punch test simulations for the determination of GTM parameters, Gerson-Twerger-Needleman damage parameters. And after that, we used compact tangent test simulations for the determination of fracture toughness values. First of all, a few words about the small punch test. This is a standardized material testing method where the sampling can be done during operation of any engineering system, for example, nuclear power plants as well. And after that, the sample, a small thin circle, is placed between a lower and an upper die, and the hemispherical ended punch is forced through the surface of the sample until fracture. And from this material test, multiple valuable material properties can be obtained, like ultimate tensile strength or creep properties as well. In our study, we used two main approaches of crack simulation methods. The first one was the virtual crack closure technique, the VCCT method, which is based on the linear elastic fracture mechanics. This model is based on the assumption that the energy released when a crack propagates a certain amount is equal to the energy required to close the corresponding sized crack. And this model also assumes that the crack propagates through a predefined crack path. This model can be used for brittle fractures mainly and for multiple material models. The other one was the cohesive zone model method, where we assume that there is a softening zone at the crack tip, where the opening of the crack is resisted by cohesive tractions, and the propagation is ruled by traction separation laws. Here, both the crack initiation and propagation can be simulated, and the sum of energy absorbed can be calculated as well. As the fracture toughness determination is always connected to some kind of large strain simulations, we had to determine some kind of damage parameters, for example, Gerson-Twerger-Needleman parameters. And for that purpose, we generated flow curves from our tensile tests, which we put into our simulation model. And after that, we generated 90 different GTM parameter sets to train our artificial neural network system. And with the help of the ANN, we determined the best fitting simulation curve for the small punch test measurement. And this way, as an inverse method, we got the best Gerson-Twerger-Needleman parameters for our investigated materials. But after the first preliminary runs with very simple small punch test geometry, we saw that there were some scatter in the measurements, and also the sample thickness reduction was not monotonic at all under constant loading. Therefore, we knew that there were some micro displacements in the measurements. So we decided to use springs in different points of the simulation model, and also we used some kind of collision surfaces. And we also taken into account the punch deformity as well. After that, we came out with an average geometry for our four investigated materials, B, G, and the irradiated B and G materials, in terms of spring forces and collision surface gaps. After that, we set up an evaluation criteria based on the force equality at the failure of the small punch specimen, and both in the simulation and the measurement. In the simulation curve, we can show that failure point when the first element reached the failure void volume fraction, Gerson-Tvergar-Needleman parameter, and therefore it disappeared. And with that evaluation, we acquired 4 different GTM parameter sets for our 4 material. And also we saw that the displacement scatter wasn't relevant at all with this evaluation criteria that we used. In the beginning of the study, we wanted to compare our fracture toughness results with the real measurement, but we didn't have any measurement of GR curve. Therefore, we had no fracture toughness values. Because of this, we had to estimate the fracture toughness values with the standardized calculations from Ashman, as you can see the standard. And for that calculation, we only had to use master curve reference temperature T0 from 3-point bending test measurements. We also use the RMSD value estimate by that value that you can see for a steel material. It's very common. And with that calculation, we estimated the fracture toughness values for our investigated materials. After that, we built our compact tension test simulations. For this simulation, we built a 2D plane strain mesh with a very fine element size with the crack propagation area. And in this model, we combined the VCCT method with the GTN method. The VCCT method mainly focusing on brittle cracks, and the GTN method focusing on ductile cracks. We wanted to highlight the advantages of both methods. And therefore, we ran simulations with constant loading to evaluate our results with the plain VCCT method. And also we ran simulations with the loading and unloading scheme to be able to evaluate our results with the standardized calculations. From that simulation, we done this to both of our unirradiated materials, and they came out as a ductile crack. We could estimate the fracture toughness values, and there you can see the comparison with the estimation. We done this also to our irradiated samples, and in the case of the material B, it came out as a ductile crack. We also got a fracture toughness value, but at the irradiated G material, there were cleavage, so we knew that this was a brittle crack, therefore no fracture toughness values can be estimated or calculated with this method. After that, we wanted to connect the VCCT model with the CZM model. We wanted to estimate the cohesive energy and stresses from the VCCT method. And therefore, we illustrated the J integral values in the function of energy release rate. We both done this to the plain VCCT simulation and the connected VCCT plus GTN simulation as well. And on the connected simulations curves, we saw that there were 2 characteristic points that can be connected to the critical void volume fraction and the crack opening of the simulation. And after that, we used these J integral values, projected that to the plain VCCT curve, and we got 2 characteristic energy release rate values. I marked the relevant values with the red dot, as you can see on the slide that we used. Under the lower value, it was a brittle crack, but after the higher value, we got a ductile crack. We done this to the B material, unirradiated and irradiated, and we also done this to the G material, And we also saw here that after a very short simulation, it came out as a brittle crack. So we also got only one energy release rate value. After that, we built our simulation model for the CZM method. Basically, it was the same mesh that we used at the VCCT plus GTN simulation. And as I said before, we got the cohesive energy and stresses and the max cohesive stress parameter from the VCCT plus GTN model. We used a linear law and a trapezoidal shape for our simulations. We ran the CZM simulations for the ductile cracked samples, and we estimated our fracture toughness values. And here you can see the comparison from the CZM, the VCCT, and the estimation from the standardized calculations. It was a pretty good agreement between the results. So as a conclusion, I could say that we used a small punch test simulation with the help of the artificial neural network system to determine GTM parameters for our investigated material. And after that, we connected the VCCT plus GTM model to highlight the advantages of both methods. And with the combination of these two methods, with this modeling technique, also the ductile brittle transition and the crack propagation can be handled. And after that, the determined GTM parameters were used for the VCCT plus GTN simulations and the CZM simulations to acquire fracture toughness values. Thank you very much for your kind attention.